Okay. All right, so as you've seen, the exams are all graded, so your scores are in Canvas. I redid the homepage, so on this, you can either find in exam 2, it will have each of the exams, and then you can go through the solutions. So do use this to make sure you understand what you did incorrectly, to be able to do well on the final, which will be Wednesday, what's it again? October, it's coming up. October, when is, October 1st? Yes, so Monday, September 29th is going to be this third exam, and then Wednesday will be your final option, and then Friday is going to be your final project. So for the final project, it is, I haven't written it yet, but it will be basically a simulation of a project. So you can choose whether you want to do something you've already done, which is the LED lights with the thermistor or photoresistor as your input sensor. In lab, next week you're going to build a comparator to be able to now hook up all 3 parts together. So you would have the input piece, the comparator, and the output piece. With the digital logic, you can add in digital logic if you would like to that simulation also. The idea is that if you pick something in 1235, you're going to also add onto that something with timing with it. So you'll have a time-dependent element within there added in. And so doing the simulation now will make it much easier. You can do almost the same project for the final in that lab itself too. Does that make sense, kind of what you're going to do? Okay, so a simulation is all that you're going to need to do for the final project, and then we're going to present those in this class on that Friday. And it will be very informal. You know, here's my computer. Here is what I wanted to do, and this is my result of the simulation. That's all it's going to be. So very, very informal, and we'll move really quickly. We might break up into groups and have you just show each person in your group because we have so many people. We'll see how the timing goes on that for Friday, on that Friday. Okay, so try not to stress about it, that it shouldn't be too big of a deal, but the bigger part is just doing the simulation portion of it. So some of the work we'll do today and that you've done in lab can be used towards that final piece, okay? All right, any questions? Yes?
Would you be able to check out the lights?
Yes, thank you. Maybe not. There we go. Thanks for reminding me. All right. Okay. All right, so we're moving into sequential digital logic. All right, so last time, weird. There we go. Last time we talked about digital logic, and that was called combinational logic, where we have the fixed gates. And today we're going to talk about a little bit different, a little bit more combinational logic first, and then we're going to, shouldn't say simulation, but the annotated one. We're going to talk about the 7-segment display, which can be also a fun thing to add into a project if you would like to. Understanding both asynchronous and synchronous sequential logic, and then asynchronous application. We're going to talk about a remote controller. We're going to talk about clocks, latches, flip-flops, and registers, some basic sequential logic circuits, and kind of how you would design. Actually, we're not going to do finite state machines today. Just ignore that one. And then some more sequential circuit. So a 7-segment display, you guys have seen them, hopefully, on digital clocks. That's the display that it has with your number that's on there. They have much nicer ones than they used to have. Each segment of that is a number A, or a letter A, B, C, D, E, F, G. And depending on what number you want, depends on what light would come up. So if I want a 1, I could do F and E would light up to give me a number 1. Or you could do B and C depending on which side you wanted it on. So that would be F and G or B and C lights would need to be 1 or B and C. To do a 2, if I can draw very well, this would be A, B, G, E, and D. So go ahead and fill in this truth table. I already put in the, we are going to simulate portions of this. Okay, I know what I was going to do now. I already put in the numbers, so 0, 1 would be that one. And note that these binary numbers correspond with the decimal number itself too. So if you were to convert it over, I would have 2 raised to the 2 for 4, plus 1 for 5, and so on. So go ahead and put in the output of what you would need for 1s, for A lights to make a decimal 0, and then for decimal 1, we went over that. So you can pick whichever one you want to pick on those. So go ahead and work on filling in this truth table. So your output will be a 1. Your output will be a 1 if that's the light that you want on. So to make a 0 would be the whole outside. So A would need to be 1, F would need to be 1, E would need to be 1, D would need to be 1, C would need to be 1, and B would need to be 1. So all of them would be 1, and then G would be a 0. Does that make more sense? And so I'll do 1 for you also. So I'm going to choose, trying to think which way does it light up usually, B and C. So that would be B and C would be 1, everything else would be a 0. And then for 2, I would need A, B, G, E, and D. And so C and F would be off. Okay, so keep working on that and fill in the rest of the table. All right, so as you can compare your table with this one and make sure you were able to achieve the end truth table. So each one of these A, B, C, D, E, F, and G is going to be considered an output. So in order to create each one of these is different outputs. So I need to use X1, X2, X0 through X3. So all 4 inputs produce each one of those as an output. So, oops, give myself more room. So last time we talked about how to create from a truth table the logic for it. So we would select which one we want to tackle first, and you would need to do this for each one of these. Anybody have a preference which letter we want to try first? Well, as far as A, B, C, D, E, F, or G. So you're going to code for the output, which would be one of the lights, not all 8 of them. So A, B, C, D, E, F, G. F. Okay. So let's pick F. So with F, each time you have a 1, we're going to write the expression, which would be X0, X1, X2, X3 bar on each one of those. This one is going to be X3 bar, X2, X1 bar, X0 bar. This one is going to be, I should write it as I'm going, so right off to the side, maybe not. And then all of these would be ANDed together. So for this next line, you're going to have X3 bar, X2, X1 bar, and then X0. And then for this next one, X3 bar, X2, X1, X0 bar. And for this line would be X3, X20, X10, X0 bar, sorry. X3, X2 bar, X1 bar, X0 bar. And then for the last one, X3, X2 bar, X1 bar, X0 bar. So now you have all of the terms that are 1, and then we create the function for f is going to be all of those ORed together. So I'm just copying down the terms. So 1, 2, 3, 1, 2, 3, it's 3 bar. And so I just need to check that I have all the terms in here. So I have 1, 2, 3, 4, 5, 6. I should have 6 terms, which I do. So now you can do a little bit of Boolean logic or algebra. Let me put it here. So any terms that are these are going to be the most common. You can factor out, just like you do with numbers, you can factor out the variables. So, for example, on any that have similar variables, when we have 4, we need to have 3 of them be the same and 1 would be different. So we can see if we have any of those. So in this first one, we notice that these 2 are similar. The only difference is that one of them is x2 bar and the other one is x2. So we can factor out the common variables. So these are common with both, and then this would be an x2 or x2. So if I have the variable ORed with the opposite of its variable, what would it be? It's always going to be true, right? Because if it's 1, the other one's 0, so I'm going to always have a 1. So this would be always a 1. And then 1 ANDed with a component or any variables is always also going to be the variables, because it's going to depend on what their values are. So that is what these properties mean. So when I have a or a bar, it's always going to be 1. Or if I have a or a, it's always going to be a. Hopefully that makes sense. And then when I have a ANDed with 1, it's always going to be a, whatever that variable is. When I have a ANDed with 0, it will always be 0. A or 0 is a or 1 is always going to be a 1. Note that this is the one that's usually not normal, because we have a or 1. It will always be, the or value gives it the 1 always. So that one's not normal like our normal algebra. Otherwise, this looks like normal algebra. Like, yeah, when I multiply it by 1, it's 1, or it's the value of whatever it is, which is a, and if I multiply by 0, I've got to get 0. So those look the same except for that one condition. So using that property, we can kind of reduce this down a little bit. Do we see any others that have 3 components that are the same? What about this one? No, not that one. X1, 2. So those 2?
Yeah.
So the difference in these is going to be the x0. So we can do the same thing. And it would be x3, x2, x1 bar. And then this becomes a 1. And so it's going to just end up with these 3 terms just like that one. And then, yeah, the other one is not able to be factored. So you can also, so looking at these, you could take x3 bar, x2, and then these 2 components are opposite though. So this would be like our normal factoring kind of way we would do it, where we would bring it out. Does this reduce this circuit? Not really. So whether you do that or not, it doesn't really affect it, in my opinion. So the next thing you would do is then take the reduced expression, and then we're going to create the logic for just that one light. So I'm going to assume I have 3 input and 4 input gates, which you'll see when we go to the simulator you don't have. So this first one is going to be inputs of x0 bar, x1 bar, and x3 bar. And we get x0 bar by putting it through an inverter. And we would do that for each one of them. And I'm just going to label them so I don't have wires going everywhere. When you actually do the simulation, you would wire them directly up. So you would do these for each of the elements, or each of the variables. And then the next one is going to have a 4 input. For x0, x1 bar, x2, and then x3 bar. And this one's going to have 4 inputs, x0 bar, x1, x2, x3 bar. And then the last one will have that x3, I'll go with the same, x1 bar, x2 bar, x3. And then each of these goes into an OR gate. And this would be my F. And I would tie that to the light of the F. So you'd have to do this for each of those lights. Okay, questions? So there's a nice chip out there that does this. So if you do want to use a 7-segment LED display, the chip internally has all this logic in it already. So you can just put in the 4 inputs or 3 inputs, whatever, however many inputs it has, and then hook it up to a LED display light, and then it will drive it. So it's good though. I thought this was a good practice to do. You can go and simulate this now if you want in the CircuitVerse or in LT Spice. So questions though about it? Okay. All right, sequential circuits is where you include memory. So there's 2 types of memory. There's going to be, or there's 2, when you add memory, there's going to be 2 types of configurations. One's asynchronous and one is synchronous. For an asynchronous, it's going to change right as you apply the input. So the minute the level changes, it's going to create an effect. Synchronous has a clock that when the clock happens, it will change at the clock timing. So it will only change once a clock happens. So that is the big difference between the two. So there is a clock. So that discrete time interval is on a clock. All right, so thinking about a remote controller. So we have memory in the remote controller. When I turn on my TV and I am on a channel when it turns on, and if I want to go up, so it has internally some memory to know where I was. It's going to keep that memory stored here and say I was on channel 3. So if I was on channel 3 and I click it to go up, so I go up, I expect it to go to channel 4, and then I want this element to know now, like, okay, now it's 4, and it's going to store that information in there and keep it for a minute until I make another change. So say again, I hit up button again. This is now going to change to 5. And then this will also change to 5. So this is how these work. Does that make sense? So you need to have some way of internally storing that number, 3, 4, or 5, based on what had happened before. So we call these different states. So we have a current state and kind of a next state. So when you have a clock in there, it's going to be the next state. If you have it asynchronously, the minute that you press on the button, it is going to change and you won't have a clock. Does that make sense? Some yeses and nos. Okay. So these memory elements can be different kinds of memory elements. One is called a latch. And this will be a basic memory. You then also have what are called flip-flops, and then also registers. The way I like to visualize this, that moved, okay. Go up. Don't know what happened to, there we go. Okay. I don't know where it happened to those. Okay, so I kind of think of a latch as like a sticky note. So the latch can take data in, but it's only, so you can write on it. It will stay there till you erase it or you kind of pull it off. It will remember that piece of information as long as it has is powered on. The minute it turns off, it's not going to keep that memory. So it is called a latch. It will be based on the control signal. So if I change it, it immediately changes. So that's why you see this little sticky note. The flip-flop, on the other hand, will keep that information in it. So it has a lock on it. So you can think of it as more of a locked diary. It will keep and retain that information until I open it up and change it. So it will then change that based on if I open it. So a flip-flop locked diary, you can only write at a precise timing when it's open, and then it will stay unchanged unless I write something else, and then it will do it on a time frame. A register is going to be a filing cabinet of these flip-flops. And so it will be like a filing cabinet of the diary where I can open all my drawers at one time, and then I can store the whole information in one time. So these are going to be different lengths. So a flip-flop will be what's called a bit, and a register is going to be what we call a word in binary. So one piece of data, or if I want to have a whole bunch of them, it creates a word, and it's multiple amounts of them. Does that make sense, kind of what a latch, flip-flop, or register is?
So does a flip-flop not need powerless?
So they all need power.
Or I mean, like, once it's turned off, the power's turned off, is the data still safe?
So it depends on how it's made. I'm trying to think of an easy answer. For now, think about a yes. It will store that. That would be an easier answer for now. So typically when you turn on these flip-flops, like if you build them, you set them, and then, so you use a button to actually set them, and then you will run after that. Okay. So those are the memory portions of it, and then the other thing we have to understand is the clock. So when I talk about a clock, I'm not talking about a digital clock like you're used to, so not this kind of a clock. So we are talking about the clock that is actually creating a pulse. So we want to have an element that creates this kind of a clock. So we can use a chip to actually create this clock. It's called a 555 timer chip. There's other ways that are a little bit, it's better to use an actual crystal, which is a physical rock, a quartz, yeah. And so it will oscillate, and you can create a clock based on that material itself, which is going to be way more reliable than the 555 timer. So you can buy them as a chip, and you buy the oscillator chip based on whatever clock frequency you want to create. But this is nice for you guys to understand how to build these, because they're kind of fun to play around with. You can create a clock from them, or you can create a timer from them, where you can have an event happen, and then after a certain amount of period of time, you want it to like turn off. So this would be what this is the most useful for. So they're useful chips, so I kind of wanted to describe them and kind of go over a little bit how they work. So these came in your kit, so it's an LM5555. Today we're going to actually simulate them. And so in the data sheet for these, they gave you a nice drawing already that says hook it up like this to create your clock. So there's two types of ways of operating it, as I said. One is this astable. And for the astable, this creates a clock. The other way is where you're going to create a time frame of when you want it to be on, and then it will turn off, and that is called monostable. So this one creates a time period. Okay, so the first one we're going to do is hook this up in your simulators. So go ahead and get out your computers, and for those that have installed LT Spice, you're going to be running LT Spice for this one. The chip is NE555, and then the elements you're going to look for resistors, R for resistor, and then LED for the light, and C for capacitor. So if you don't have LT Spice on your own computer, please meet your neighbor that might have it on their computer and kind of work together to create this.
So what's the diode and resistor on the output?
So 510.
Okay, yeah, but what are the parameters for the diode?
So for the diode,
Or I guess
so just look for LED, and it will just be LED light emitting diode. Is it not finding that on yours? Are you on something else?
no, I'm using Optic Spice. Just in the past, when I tried to simulate, it's wanted me to select a specific part of the model.
Yeah. So the diode will make you select a specific one, but the LED will let you run it. It just does a default, which is not accurate, but it will just let you run it. But yes, with the diodes, it will because your drop is different. But this one, it works. So, yeah. All right, so get a little smaller. So let's simulate this one first. So ground, you're going to put to a ground, and then you're also going to connect the power supply to ground, and then also to the VCC pin and to the top of a resistor that's 10K. And then your DIS is going to be in between these two that are 10K, and your threshold will be right above this capacitor, which will start at 47 microfarad. So the capacitor, if you build it, in the notes I have some information on those. If you do want to build that, we're going to learn about the capacitor in 1230. It's a time-dependent element, and this also helps to, you'll see as we make the change here that it changes the timing of it. And so right now that's all you need to know about it. It's another element that is time-dependent and so creates some timing. This one will be 0.01 microfarad, and then your output will have the resistor to the diode. And then if anybody is on a Mac, to create the SPICE directive, I do a double click to get this. It's under draft SPICE directive, or a Shift S to get the directive. And you want that to be a .tran, and I do it at like 20 seconds. So you want that .tran in there. Oh, sorry, there we go. So it's NE555 is that the main box that you're looking for. So NE.
Yeah, oh, yeah.
Okay, so a couple things to point out here. SPICE, so this is based on SPICE. So SPICE uses a model that makes it very accurate. You can put in a lot of details in a model, and then it will simulate. We've done only linear models, like the resistor's linear element, but there are very complicated elements out there. So this has a model in there that tells you all the information you need to know about the 5555. 555. I say the 55 is long. And so each element uses that SPICE model, and the elements themselves, when they have a variable, voltage will always be a default of volts, so it won't have a unit to it. Resistors will always have a default of ohms. And then capacitors have a default called farads. And then for the units themselves, when you do the units, you're going to use M for 10 to the minus 3 at the end of the unit, or end of the number. So this would be 0.01 milli. It does not differentiate between a small m and a large m. So if you put m in there, it will default to milli. So I had a simulation once where I was doing mega ohms, and I did not realize it was simulating it in milliohms, and it was blowing up, and I was trying to figure out why. So be careful with that. With SPICE, it is not case sensitive. So if you put a capital letter or a smaller, it's going to look at it the same. You have to put MEG for mega. So milli, and then U is for micro, 10 to the minus 6. And then N for nano, 10 to the minus 9. Remember what pico is? 10 to the minus 12. There's a femto, which is F, and an A, which is even smaller. So most of the time you're going to use micro and milli and pico. So U would be at the end of those for your units. So for this capacitor, you want to put a 47 microfarad, so it would be 47 U on that value. Okay? Does that make sense? Okay, and then as you see here, this is 10K is going to be different than 10. So make sure you put 10K and use the unit for K. All right, keep working on building it. For those that are far enough along, when you simulate it, I like to, so we're going to want to see, for this LED, you won't see it blinking here. So we want to see that enough voltage is going across it, and/or we also want to look at the current. So I like to look at those in different panes of LT SPICE. So if you click on, some of you in the PCs may have it as a menu. For Macs, you're going to have it as a double click or right click. You can do an add plot pane. And then in the plot pane, you can click just wherever you want. So I want my voltage to be where I wired it as LED, and then you can see it pops up on that pane, the voltage. if I want to put the current in the other one, I'm going to put or click on the pane I want, and then I'm going to go down and do the current going through it so that I can look at those results. Does that make sense? Okay. And you can see I labeled my wires, so you can see here it says V of LED, so I know what that voltage means. And here you can't really see, but it says I of D1. Oh, that color's horrible. Plot settings. Okay, I don't remember exactly. I know there's a way to change the coloring, but I don't remember it offhand. So from this, we know that the diode has to have at least a volt, probably a little bit more than a volt to turn on. So on this, we're just looking to make sure, like, oh, it's on and off, and it's above 1 volt, which here it goes all the way up to 9 volts and down to 0. So this would be my clock, and I could use this as a clock into another part of the elements if I was to build this, using it as a clock. This is just to show it kind of blinking on and off. For our diodes, we know they need to be between 10 and 20 milliamps typically to get enough brightness to actually really see them well. So here, you can't see it well, but it does go up to 16 milliamps and then it goes down to 0. So at 16 milliamps, we're probably getting some brightness out of this. What would I change to make this brighter? Which resistor? So this 510, would I increase it or decrease it? Decrease it and put a little bit more current in there and it would brighten it up. What is the drawback of doing that though? It's what? Okay. So the voltage might drop a little bit more, but you have more current, which means you're drawing more power. So you're going to be consuming more power, which is going to drain your battery quicker. So you got to have that as kind of like, do I want it to be really bright, or am I okay with it less bright? So that's kind of your trade-off there. All right, make sense? All right, so make sure that you can get this clock kind of going. And then if you are able to simulate that and see both the voltage and the current, then you can move to creating the other monostable simulator. Oh, actually, and play around with this. So this one is 47 micro. Let me move over.
How do you specify like micro? That's
The U?
it's U.
Yeah. So if I change this to 470 micro, I put 470U, and U is for that unit. And then it writes it out better there. So if I change that and resimulate it, what happened? Did you guys see the difference?
Yeah.
So I'll go again. So this gives you an idea like, oh, if I decrease my capacitance, I get a faster clock. And if I increase the capacitance, and run it again, I get a slower clock. Yeah.
So is the capacitor just like storing energy?
Uh-huh. So in 1230, we'll talk about the capacitor, and then actually how to, if you want to, you'll learn on how to actually create this timing. And it's R times C. So you kind of work on figuring out if I change that C, I fixed my R and I'm just changing my C. And that increase or decrease, and why is it making it faster or slower? So we'll talk about that in 1230. But for now, understanding like, oh, well, I just want a specific time, a clock that's fast. I can decrease that and make it faster. Okay? All right. So just make sure everybody can do this, and then once you've gotten that simulation, and if you want to play around with some of the other values to understand more what they do, feel free and see the effect that it has. And then you can go ahead and go simulate the other one.
So for me, it should, if I just think of it, I guess that's because everything is try to see.
Yeah, I get taxation.
Oh, that's fine.
Tax days.
I think it's F. It's like all of it is that's so accurate. Why did they make it so oh,
So, the whole point of a recessing is that you can reset. So you can get it 500. That's the purpose of it. Yeah. So, the dash number is really just saying, for her, she has a reset stream, while this device only has a active low reset. What that means is when you set it to the ground, then it resets. So you want to keep that at 9. But it's dash because it's like it's something that you can't change. But for now, just set it to
Oh, she's super long. How do you have to do this? Oh, yeah. Ah, all right. Yeah, now I see it.
All right, so for this one, you're going to want to put a trigger for this one, so you have to put a pulse on that. So on the diagram, let's see, where's the- on the diagram for this one, for the monostable, it's a push button with to a 10K that then ties it to a high voltage. This is called a pull-up resistor. But in order for it to work, it needs a little bit of a trigger, which is why it's labeled trigger. So to model that in PSpice or in Spice, you're going to use that pulse function to basically trigger it. Okay? So the pulse function, you can look up for the LT Spice syntax of it. It's the voltage on, the voltage off, and then the time delay, and then how much time it takes to rise, to fall, and then the full length of time you want your whole pulse to be in is the period of it is the last value in there. Okay, so that should work to get that pulse to trigger it instead of putting the push button and the 10K, which is hard to model in PSpice or LT Spice. So it should look like this for your monostable. So go ahead and work on getting this one, and then again change that capacitor from 470 micro to 47 micro. See the effect it has on it. And in this one, I'll simulate it really quick. So you're still going to do that output, and then if you want to look at the current again through it, it'll be, oh, I put them together. Okay. So you can see that it gives you a pulse, and then once it's triggered, it basically stays on for close to 5, or let's see, I guess it starts about 1 and then goes to 5. So it's about 4 seconds. And then for 47 micro, you can see it's much shorter. So make sure you can do it and play around with that for a minute. I'd label mine so I can know. You can just click on the, it's easier to just click on that. So when it's the little arrow, it means it's gonna be current, and when it's that, or when it's a bullet, it just says. And so you can see your time frame isn't long enough to really see the whole thing, so you're gonna wanna change your time. Good things for me to point out. So I forgot to also mention, so you can find the traces if you label the wires. You can find them. I find it typically easier in LT Spice to use the little probe. So as you see when I go next to a wire, it has a little probe. That's like a digital multimeter probe, red. And so wherever I click, that's going to compare it to ground. I can also, when it changes to the current, that means through the element, I can change, do it here. There's some SPICE directives where I have that dot tran, that means I want to run a transient. You can do a dot mesh, which is going to do a measuring. So if you want to actually do like power consumption in elements, so I will put together a little sheet that will have the syntax of these that will be a little bit easier for you guys to look at to do some of those, and then you run them at the same time as this. So that's usually, I like to do it that way. I think it's a little easier, but you can, go in and actually add your trace, but you have to know which number your wire is, and that's sometimes hard to know. All right, play around some more with that. It's a combination of the RC, so the R5 and the so the combination of those two is what is creating that. So when you have one fix, then you change the other. It's increasing or decreasing the time it takes to charge and discharge. Yeah, it's creating that.
It's some PS2. I should just go on the it should still work. Oh, yeah, it's true. Maybe it is testing your What about just evaluate?
Yeah, it's evaluate. I think it was a similar thing as well. Yes, yes, it was very similar. I always felt like I don't want to like go past that. So actually. It's not and it's like
It's just a warning.
So a couple people were asking me about how to put in this pulse directive. It is where you normally have the voltage. So you can just click on where you would normally put in your value, your voltage value in DC, and just type that command in there instead. So instead of, like, a lot of times you may have 5 or 5 volts, that's where you're going to just replace it with that whole command of pulse. And you can do sinusoids the same way. You can put sine and then that function. Anyway, okay, keep working for another couple minutes. Make sure that you can do both the long one and the shorter one. A lot of people are getting a pop-up message when you run this too. Just ignore that one. It's a log file, which means it's written down information in it. So when you do a .mesh, it will have in that log file the actual values of what you would ask it to measure in there. So it's not an error message, which I know a few of you thought they were error messages. So just, you can close it out, or you can just move that window over to the side. It's called a log file that just keeps the information from what it's running. Somebody was showing me on their PC, if you're using a PC, it does have a nice thing for the pulse. You can put each one of these and it tells you what each one of those does mean. Macs, not as nice, but still works.
Because it would describe why you would see this. But in general, it's all.
All right, we'll work on this for maybe a couple more minutes.
Isn't the idea like you apply power and then you press the button and
Okay, any questions on this? You guys good? Kind of fun to play around with a digital component, hopefully. So the 555 timer, the circuit verse unfortunately doesn't have that model to be able to describe it in it, so that's why we're doing it in LT Spice. So if you want to do more simulation, you can continue to do more simulation with that one and play around with it. If you want, you have all the components in your kit. You can also go and build it and actually physically see it and see the clock running on it and the light actually lighting up and going off. So if that sounds fun to you, you can do that. Again, you can use this as part of your final build design or as part of your simulation for your final project in here. All right, so moving on to the next process, which is to understand the full design of a little bit more complicated digital system. So the design process for a little bit larger digital system is to draw it out as like a flow diagram. So you could understand, if I have this input, I'm going to then go and do this or this. So they're called state diagrams. You can either create the table first and then the state diagram, or create the diagram and then implement the table from that, whichever way you feel is easier. They're both ways of visualizing what is going on. You need the table for sure to then be able to implement the logic needed for it. So if you don't draw the diagram, it doesn't matter if you have the diagram, but I find it useful to like visually see how things are flowing in a logic circuit. Once you get that table, then you're going to do the digital logic that we did for the LED light, where you're going to identify the inputs, identify the outputs, and then do the combinational logic for that. The difference with sequential is there's going to be one more step where you actually add in a flip-flop, and with that flip-flop you have the input, which is the old state, and then it becomes an output is the new your next state actually comes from the digital logic, and that goes into the flip-flop. Once the timer or the clock goes, it then changes the output of that latch. And so anyway, it'll be easier to see it visually, I think. So what we want to do is design a digital lock that opens with the sequence of 1, 0, 1, 1. So when I've entered 1, 0, 1, 1, it actually unlocks the lock. So that's when I'm going to get my 1 value, which then triggers whatever lock element that I have. So with that, I made notes on the side of this one. I have a current state, and then I have my input, and then I'm going to go to my next state. So for my first one, I don't know what has been pressed in the past, so I'm at a current state of 0, S0. If I have a 0 or 1, if I have a 0, that means that I need to wait until I have a 1, because my sequence again is 1, 1, 0, 1, 1. So this means that I don't have anything, I haven't started it yet, right? So it's going to wait and wait and wait till I get a 1. Once I press a 1, I'm going to see if my next number is a 0. If it's a next 0, then I'm going to have 1 0 in there. And I'm going to see if the next number is 1. If I get a 1, great. If I get another 1, then I'm done and it will open. So that means that I had, my input was 1, and I went to state 1. So my state 1 means that I received a 1. If I am in state 1 and I get a 0, that means I need to move on to the next state of 2. If I have gotten a 1, 0, that means, and I get a 1, then I'm going to start over and be at this place again. So if I get a 1, 1, that still means like, oh, I can start over at the 1 again at the very beginning. Does that make sense? How this is working? Okay. So I get 1, 0, 1. I'm at state 2. That means I've received a 1, 0 now. So that means I'm here. So if I get a 1 here, then I'm done, and I move to the end state. So that would be this one. I got a 1. So I go to S3, or state 3. But if I get another 0, if I get a 0 there, then I have to start all the way over, because that's not any combination of 1, 0, 1. So I go back to state 0. If I did have that 1 and I move to the last one, I'm waiting for that 1 also. If I get 1, then I go to state 4, and my output will be a 1 there. So I'm only going to get an output of 1, which unlocks it, when I have all of those states, 1, 0, 1, 1. I can then draw this, and this is called a state diagram. So I put my states in the circle. And we saw, like, if I get a 0, then I'm going to just stay in that same state. If I get a 1, then I'm going to move to the next state. If I'm at state 1 and I get a 0, that means I've gone 1, 0, I move to my next state. If I got 1, 0, 1, that means I move to the state 3. And if I get 1, 1, 1, that means I move to state 4. And my output is 1. So the first number in here, or the first number is my input. So this is considered my input, and this is my output. And so along each choice of this flow diagram, it gives what the input was and which state would I have to go to. So this is called a state diagram and helps to visualize visually what is happening in the logic of what's going on. So you can see that as I get more and more complicated, these state diagrams are going to be very, very big and get very complicated. I would probably not want to use discrete AND gates and OR gates to implement a huge system like this. So at this stage, you would go to a programming language and actually program it in and have the program use a synthesizer to actually create your logic for you. And that's what an FPGA does. So you code in a, it's called a register language. Verilog is one of the names of one of them. VHDL will be another one you'll hear, but Verilog's more common now. So you use this programming language to describe what's going on with the state machine, and then it will synthesize onto an actual hardware device all the ANDs and the OR gates for you, which makes it great. So that's what 37 is. It's at 3700, you learn how to do that next step on this. You learn how to get more complicated state machines, and you learn about techniques on making these optimized and making them a lot more, optimizing them. And then you learn some other techniques in there too. So that's what 3700 is all about. So if this has seemed kind of fun to you, then that might be a class that you want to take for EEs. If CEs, you have to take it, and it's super fun because you really like it when you get into it. So from here, we go back to the table, and in the table, we define the inputs as our current state and then that input that's pressed. So these would be our two input columns. And then this is now considered an output. And then this is also, going to be an output. Oh, that is not very bright. There we go. So as you can see, the next state has 3 digits to it, 3 bits. So we're going to need to have each one of those as its own output. So for example, I'm going to call this first column N1. And here I called the first column of this one C1 for current state. So that would be, we have 4 inputs and 4 outputs. So we would do the same steps here as we did for the logic on the other 7-segment display. So we're going to create the expressions, which I already did, and these can't be reduced down any more than this. So from these expressions, we're going to add in the memory. So how you add in the memory is this D flip-flop is one of the options. And so this is what the D flip-flop looks like. You have an input D, a clock, and then an output Q and an output Q bar, which those two will just be opposite each other. So with this, you're going to again have 1, 2, 3, 4 inputs, C1, C2, C3, and X. And the flip-flop is going to be as many flip-flops as you have from a current state to a next state. So you have to hold that state, you know, that bit in there before you know what it's going to change to. So for each one, between your logic, which here, this would be my logic for next state 1. So this would be N1. So just not doing it. This wire right here is called N1. And N1 was just an AND gate only, 4 input AND gate of C1 bar, C2, C3, and X. So my C1, C2, and C3 actually come from the output of the flip-flop. So, sorry, I put CS1, I guess it should be C1. So this output of C1 actually comes as the input into, move it down so you can see better. Okay, so the output is C1 bar, so I could use the Q bar on that one instead of having it come from C and then doing an inverter. And that goes in as an input into that AND gate. Then I have C2, C3, and X goes in there. And the output of that is that N1. So it basically has its own feedback. So the next one would be to give me N2, which would be here. I would so this wire is going to have all the logic from that equation. So this logic here. So I'm going to have 4 AND gates that are 4 inputs each, and then a 4 input OR gate in that box. And then these wires are coming from, this one is going to come from up above, from the C1 of that D flip-flop. C2 is going to come from this one. From this flip-flop, and then C3 is going to come from this flip-flop. Does that make sense? Yeah.
What's the purpose of the feedbacks?
So it's just keeping, so that flip-flop is like a memory, and so it's keeping that number in there. So that, you know, when you clock it, it's going to change based on the input. So here, my next input then becomes my current state. So with the clock, that input comes the current state. And so as I move through each of those states, back to this one. So to move from state 1 to state 2, I need a 0. So if my input is 0, it's going to move from state 1 to state 2. And so I need to keep in memory that value of that state 1. Does that make sense? So, but we have to break it up into the digital logic portion of it. So we coded the state 0 was actually when I have 0, 0, 0 in those flip-flops. And then to move one of them, I created that logic to move it from one to the other. Does that make sense? Okay. So anyway, you can keep going through each of these, and then Z is going to be the C1, C2 bar, C3 bar, and X. So that would be my final output there. So this would be in the simulator, it would have a whole bunch of logic in that N2 block and in the N3 block. And you could create this digital lock. So this is also an option for a final project in here. If you want to work on this and actually do the simulation for it, that would be your final project too. So that's an option if you want that one. Or you can come up with your own and work on that one. So questions about digital combinational logic or digital sequential logic? Yes?
Can you repeat where you're assigning your n values from the table?
So I called the next state.
Okay, yeah.
So I coded these as, so the state is the same. So this one is 0, 0, 0, 0, 0, sorry, that should be 1. Okay, so my N3 is wrong. So note that. It should have been a 1. Okay. So N3 is not this one. So make note that that one has an error in there somewhere. Which one is that? That is with an input of 0, 0, 0, 1. So 0, 0, 0. So you need one more in there. 0, 0, 0, 1. Okay, so that has one more in there. And then you could combine these two together. Yeah, so little error on my part. In the simulator, I would have caught that, oh, that's not actually giving me 1 when I have a 0, 0, 0, 1. So I would have caught that there. But anyway, it is from that next state. So with the next state, instead of S0, S1, I'm using my next state as 0, 0, 0, 0, 0, 1. And so I'm using the current state as an input to get that next state output. So I called each one of those bits, the first one N1, second one N2, and the third bit N3. Does that make sense? Okay, so for the exam, I'm going to expect you to kind of understand this process. I'm not going to make you draw a state diagram. I'm not going to make you do the state transition table. I will ask you how to implement that with the actual gates, so that is something I could ask. I did not get time to create your Unit 3 practice problems yet to give you an idea of what depth you'll need to know on these. So no quiz today. As you probably saw, there was no quiz posted. So no quiz today, no attendance today. Over the weekend, I'll make sure that that gets up so you'll have practice problems to work on. And then you will have an attendance quiz on Monday and Wednesday and next Friday. Okay? All right, any questions? All right, we're going to end today because I have pretty much completed what I need to.